So today we're going to talk about the Doppler effect, and in particular we want to eventually derive the relativistic Doppler effect. So you'll remember from the last video I showed you this this equation here, or this factor here, which I refer to as the alpha factor. Now historically the term gamma has been used. Okay, gamma is 1 over alpha, alpha is 1 over gamma. Yeah, I know this is really confusing, but in the frequency domain it's actually much easier if we talk about the alpha factor, which is this this factor right here. And the velocity here, this v is velocity of the thing which is moving, and c is the speed of light. So that is just a recap of the alpha factor, which I eventually put into my modified unit analysis specification, as you can see here. And so basically what I'm doing here is I'm building up a specification. I'm giving you my constants of nature, I'm giving you my equations of nature, and my definitions, of course, my unit analysis, and now we've got at least the first iteration of relativity in the specification. But before we talk about the relativistic Doppler shift, the Doppler effect, we have to talk about the non-relativistic Doppler effect. Now this is depicted in this figure. What's depicted in this figure is a transmitted frequency. So this is a transmitter in the middle here. This transmitter is moving in this direction with a speed of v, a velocity of v with units meters per second. And so this guy is moving this way, okay? And so what is received over here, so these are detectors. There's a detector over here, and there's a detector over here. And so if this guy is moving this way, then this guy is going to see a lower frequency, and this guy is going to see a higher frequency. And so this little slide here is from www.sciencedirect.com. Okay, and so this, I just found this randomly. I was just doing a search for different websites that talk about this, and this came up. And so here they say that the equation to calculate the non-relativistic Doppler shift is this right here. So if the target is moving this way, then Science Direct says that the equation to calculate the, which would be a blue shift, is the frequency of the transmitted frequency is equal, the frequency that is received is the transmitted frequency times 1 plus the velocity of motion of the transmitter plus the, or divided by the speed of light. And so this is what Science Direct says. So there's a bit of a conflict, which I will show you, which through my research I keep seeing people doing it wrong. Not everyone is doing it wrong, but it is being done wrong in some places, and so you will see that this is not exactly the right equation to use to calculate this frequency. So here is a page from Hyperphysics. So I use Hyperphysics quite a bit. These guys have never let me down. Hyperphysics, I've never found a mistake yet in their website, and so this is the equation that they say is for the normal Doppler shift for waves, such as sound waves, which move at velocity much less than the speed of light. So this is actually was written for sound waves, the non-relativistic Doppler shift of sound waves. And so here we have the frequency that we observe is the frequency of the source, okay, which is the target, the frequency of the source times 1 over 1 plus or minus the velocity of the source divided by the velocity of the wave. So it looks like this website, Science Direct, which I will link in the description, does not have this quite right, because this should be 1 over 1 plus v over c according to Hyperphysics. And I believe this one is correct. This is actually the most common way of putting it. Here is another example of non-relativistic Doppler shift by this educational source, which has classes, and this is part of their Physics 314 lectures on Doppler shift. And so they have frequency equals 1, the original frequency times 1 over 1 plus or minus v over c. So this is actually more in line with this equation and is not what these guys are saying. So there are some discrepancy out there. Sometimes it's inverted or reciprocal from what it should be. And so you have to be really careful when you go out there and looking for these resources. They might actually be saying it wrong. And so I'm going to complain about something else here. This is just something that I have a problem with in terms of the language of theoretical physics. Okay, and the language is really the mathematical language. The mathematical language can be very confusing. And so when you look at the Hyperphysics definition of the non-relativistic Doppler shift, you'll find that you'll see something like the frequency observed is equal to something and the frequency of source. Okay, so the velocity of source and the frequency of source. So in this sort of iteration of this equation, the F means frequency and V means velocity. But when you change to the normal notation of light waves, now this is the standard language for light waves. They use this symbol here instead of an F symbol for frequency. They use something called nu. Okay, so this is Latex Editor, where you type in latex and you get the symbol out. And so the Greek symbol of nu is this symbol here, and this is what they use in standard notation to talk about frequency of a light wave. And so this is what I find really confusing, because this looks like a V, even though I know it's the Greek character nu, but this looks like a V. And there's another V over here which actually means velocity, V for velocity. And this is this symbol is also a velocity. It's a velocity of frequency, a velocity of oscillations. But people like me who have a hard time processing symbols finds this very confusing, and I don't like it. Okay, so so I would prefer if we put an F when we're talking about frequency. Okay, if we put an F instead of something that looks like a V. Okay, so it makes it easier for me to understand what the equation is about. I'm sure there are lots of people out there that are like me that don't like this sort of confusion, and so V should be for velocity, F should be for frequency, and that is the way it should be written. And so that's just my little complaint for the day. In terms of the language, I find this very, very annoying and confusing. So when I write the equations, I am going to try to be consistent and always use F for frequency and V for velocity. And so let's go back to the non-relativistic Doppler shift from Hyperphysics, and you'll see that there's this equation here, and you'll see there's a plus and minus. And so there are two non-relativistic Doppler shifts. One is for blue shift and one is for red shift. Okay, when it is minus on the bottom, this is a blue shift, because minus on the bottom is going to increase the frequency, and increased frequency is a blue shift in frequency. If plus is on the bottom here, if the plus is down here, then when it's plus instead of minus, then this is going to decrease the frequency, because this number is going to get bigger. The frequency is going to decrease as you increase the velocity, and this is going to be a red shift. So if an object is coming towards you, you use this equation. Sorry, when an object is moving away from you, you use this equation. and when an object is moving towards you, you use this equation. And this is non-relativistic Doppler shift. So now I can add another equation to my specification. Last time we added this equation, which is the relativistic Doppler shift, or the relativistic frequency shift equation, and this one is the Doppler shift equation. Now what would be really nice is if somehow we could combine these two equations, because if something is moving at a certain velocity, then these two equations should be able to be combined into one, hopefully very elegant equation. And that way I don't have to write two equations in my specification. I can write just one. So here we turn to the Hyperphysics page, and now they're talking about the relativistic Doppler shift. So previously we were talking about the non-relativistic Doppler shift, and now we are talking about the relativistic Doppler shift. And so the relativistic Doppler shift combines the two equations, this one, which is the alpha factor, and multiplied by this one, which is 1 over the square root of 1 plus or minus v over c. And so that is what is going on here. So this equation here, it looks fairly complicated, but the frequency, again, they write nu here, but imagine there's a little f here. The frequency observed is this factor here times the source frequency. But this can be rearranged to look like this. And so, so maybe this is a little more elegant than this, I don't know. This can be alternatively written. These two equations are exactly the same. They're just written differently. And so this one is correct as well. And when plus is on top here, this is going to be an increase in frequency. And so this is going to be a blue shift. And if you flip plus and minus, you are going to get, if it's minus on top and plus on the bottom, this is going to create a decrease in frequency, and which is going to be a red shift. Now, something else that they do in the language that I don't really like is they sometimes write v over c, they write beta. And yes, that does look, it looks nicer in a paper. It looks nice on paper. But I would prefer to see v over c. I would prefer this to this, because this is not obscuring anything. You plug in the velocity, you plug in the speed of light, and you get the answer to the equation. If they have this, then you have to remember that v over c is beta. Beta is v over c. So this is not more elegant than this. This is not more elegant than this. It looks prettier, but it really is exactly the same as this. So I would prefer something a little more elegant. So this equation is not better than this one, so we're just going to look at these two right now. Okay, so I rewrote these in using that online LaTeX creator for equations, and so I just rewrote these. I rewrote these on the page, and so we've got this one, which is exactly the same as this one, but I would like something a little simpler than this. And so it turns out, if you do a little bit of math, you realize that this equation and this equation can be rewritten like this. Okay, this to me, so square root of, let's go back. Square root of c plus v, speed of light plus the velocity of the thing that's in motion, over speed of light minus the velocity of the speed of motion is the same as this and this. So this to me is much more elegant. This to me is much more elegant. And when the plus is on top and the minus is on the bottom, it's a blue shift. It's a blue shift. And when the minus is on top and the plus is on the bottom, it is a red shift. And so this equation here to me is much more elegant, because it encapsulates, it actually has the alpha factor baked into it. It's built in. And so, you know, to me, this is more elegant than that and that. And so, you know, what I would like to do is rewrite my specification. I would like to take this out and I would like to put this in, because this accommodates both the alpha factor and the Doppler shift all into one. So just to prove my point, what I did was I wrote a computer program, and I wrote a program for this equation, I wrote a program for this equation, and I wrote a program for this equation. And so the frequency observed 1, this is frequency observed 2, and this is frequency observed 3. And as you can see, all three of these equations produce the same value. This value is, so the resonance frequency that I plugged in was the resonance frequency of the cesium atom, which is 9,192,631,770 hertz. I plugged this into these equations. Of course, c is the speed of light, and these are the numbers I got out. So this is 15,922,105,280.911818 hertz, and this is, each of these equations produces exactly the same value to exactly the same number of decimal places. And so that is for the blue shift equation. And the blue shift equation, it's minus on the bottom of all these equations. Okay, when it's minus on the bottom, it's plus on the top for these two equations. So now I'm going to do the red shift version. So in the red shift version, it's plus on the bottom, minus on top, plus on the bottom, minus on top of these two equations. So you flip the sense of the two equations and you get the red shift. And this gives the same answer. So this is frequency observed 4, frequency observed 5, frequency observed 6, and they all produce the same value. And that value is 5,307,368,426.97 hertz. And so, and this is a red shift because this is, the frequency is much shorter than the 9 billion. And the other one is, this is 15 billion, so the frequency is much higher than the original frequency, and thus it is a blue shift. So I just want to read this one little bit from Wikipedia. Okay, it says the relativistic Doppler effect is the change in frequency and wavelength, of course, of light caused by the relative motion of the source and the observer, as in the classical Doppler effect, when taking into account the effects described by special relativity. Okay, so that's fine. The relativistic Doppler effect is different from the non-relativistic Doppler effect, as the equations include the time dilation. Okay, the equations include the time dilation, right, of the special relativity, and do not involve the medium of propagation as a reference point. Now this bothers me a little. This bothers me a little because here are the two equations for the relativistic Doppler effect, which I compressed into these two equations, right? This one is a blue shift, this one is a red shift, and the speed of light is in here. Okay, the speed of light is the medium. The speed of light is the medium. And in these equations, the medium, the velocities are being referenced to the medium. This is a reference, and so I think it's a little disingenuous for them to say that the relativistic Doppler effect is different, does not involve the medium of propagation, because the medium of propagation is in the equation. So, you know, when I hear things like that, it kind of makes me want to go, what? But anyway, so that is the relativistic Doppler effect. Okay, I can't say for sure whether this equation covers all situations, but it definitely covers a situation where an observer is moving away from you or a mover is moving towards you. This definitely covers the recessional velocities of, say, the universe that is supposedly expanding. This equation is used, and so You know, so this is actually much more elegant to me, you know, than the other two equations. So instead of putting these two equations, I can actually put the one equation into my specification, and this covers, you know, this covers relativity and standard Doppler effect. Now this, you know, may not cover all situations, all motions relative to each other, but this, you know, this gets us a little closer to understanding relativity and trying to understand the medium for propagation of light, which I believe exists, and the reason why, you know, particles can't go faster than the speed of light. And, you know, there's actually a good answer to that, a very simple answer to that. Why don't particles move faster than the speed of light? And so when you think of particle accelerators, well, what do they use to accelerate particles? They use electromagnetism. So electromagnetism cannot push particles to move faster than the medium of electromagnetism. And so it's like saying I'm running down the street and I'm pushing a cart of some sort, and I cannot push that cart faster than I can run. Yeah, maybe I could use the spring action of my arms to make it go a little faster than I can run. But in general, that cart is not going to be able to move faster than I can run. And in a similar matter, particles are not going to be able to move faster than the speed of light, because with what are we going to push those particles faster than the speed of light? So anyways, that's my take on relativity and the Doppler effect, and relativity in terms of the Doppler effect. So yeah, that's about it. I hope you enjoy this video.